grade 12, grade 10, grade 11, grade 12. Okay, so guys, yesterday we were privileged to actually get into the theorems that are centered around the center. Okay, so yesterday we looked at the theorem that says a line drawn from the center of the circle perpendicular to the chord bisects the chord. Line drawn from the center, there's the center perpendicular to the chord, there's the 90 degrees, bisects the chord. So because of this, we know AM is equal to MB. Okay, and we would write that statement, and this would be our reason: line from center perpendicular to chord. It's the acceptable reason. Okay, all because of a line drawn from the center that is perpendicular to a chord. We can then say AM is equal to MB and write this as the reason. Then this theorem says a line segment joining the center of the circle to the midpoint of a chord is perpendicular to the chord. A line segment joining the center of the circle to the midpoint of a chord is perpendicular to the chord. So this theorem has to do with a line from the center to the midpoint. Okay. What do we know about a line from the center of the circle to the midpoint? It is perpendicular. Okay. So from this theorem, the 90 degrees wouldn't be there. It would simply be a line coming from the center to a particular midpoint. And then we would say, because there's a line from the center to a particular midpoint, then our conclusion would be that OM is perpendicular to AB. OM is perpendicular to AB, and our reason would be line from center to midpoint of chord. Then there's the theorem that says the perpendicular bisector of a chord passes through the center of the circle. There is no time that a perpendicular bisector of a chord does not pass through the center of the circle. A perpendicular of a chord will always pass through the center of a circle. Okay, so that from this knowledge, this P, which is a P to the circumference, okay, passing through M, would obviously be passing through the center, and it would be perpendicular. Okay, because it is a perpendicular bisector, by nature what it does is that it's a line that divides AB into AM being equal to MB. So it being a perpendicular bisector of the chord, what does it do? It passes through the center. So encased in the word perpendicular bisector is the fact that this line forms an angle of 90 degrees with the chord, and two, it also basically passes through the midpoint of the chord. That's what a perpendicular bisector of a chord basically is. So in other words, if OP was perpendicular to AB, all right, then we'd say AM is equal to MB. Then we'd say PM passes through O. Right, so a perpendicular bisector does not pass through anything else but the center. That's basically what this thing is saying to us. Okay, so those are center theorems, okay, looked at from yesterday. Then we looked at this theorem that says the angle which an arc of a circle subtends at the center of a circle is twice the angle it subtends at the circumference of the circle. I repeat, the angle which an arc of a circle subtends at the center of the circle is twice the angle it subtends at the circumference of the circle. So we saw that there are 3 diagrams which basically outline angle at center is equal to 2 times angle at circumference. Okay, angle at center is equal to 2 times angle at the circumference. We have this first diagram which represents our arrowhead. Okay, this first diagram which represents our arrowhead. So this first diagram which represents the arrowhead, all right, has how many points or vertices at the circumference? There's 1, 2, 3, then 1 at the center. The arc that they are talking about is arc BC. Arc BC subtends this angle at the circumference. The same arc subtends angle A at the circumference. So we say the angle which an arc of the circle subtends at the center, meaning arc BC which subtends an angle at the center, is actually twice the angle that the same arc subtends at the circumference of the circle. BC is front opposite this angle. It is front opposite, so it subtends this angle. The same arc subtends angle A at the circumference. So we say the angle at the center is twice the angle at the circumference. So if this is 50, that is 25. If that is 100, that is 50. If that is 30, this is 60. If this is 90, that is 45. Okay, so basically that's what angle O1 is equal to angle 2 times angle A. That's what basically this means. Same different diagram, same meaning. Bow tie. Okay, 1, 2, 3. Vertices 1, 2, 3. Okay, 1, 2, 3. 1 at the center. So arc AB subtends the angle O1. The same arc AB subtends angle C. So this is also angle O1 is equal to 2 times angle C. All right. So if that is 50, that is 25. If that is 40, that is 20. If that is 48, that is 24. Okay, we multiply this by 2 to get that, we divide this by 2 to get that. So in other words, really angle at the center is twice the angle at the circumference. That's our bow tie. Then we have our diamond. Angle at the center. Remember that the arc here is this arc. It subtends this angle. Right? The arc is this one. It subtends this reflex angle. That's why they say reflex angle AOC. This angle, not this one. Okay? Reflex angle AOC, this angle. So that is the angle at the center that is subtended by arc AC. It subtends this angle. The same arc subtends angle B at the circumference. So we say angle AOC is twice angle B. Washing dishes. Okay, flavorful scents. You're washing dishes. Hopefully enjoying that flavorful scent of the dishwashing liquid. So reflex angle AOC, this angle AOC is twice the angle B. Okay. Then yesterday we also touched on the angle subtended at the circle by the diameter of the right angle. Remember guys that the diagram itself will not have a 90 degree. The diagram itself will have a diameter whereby we can see that AB is passing through the center. So it has a diameter, and then as I said yesterday, this diameter has to then be closed with a triangle that is coming from the endpoints of the diameter. The closure of that triangle subtends angle C at the circumference. Then we can say that angle C is 90 degrees. Remember that in the diagram angle, the 90 degrees is not there, but we say angle C, which we don't see, is 90 degrees. And the reason we say so is angles in a semicircle. There it is, angles in semicircle. That is the acceptable reason we use whenever we conclude that angle C is 90 degrees, because AB subtends 90 degrees at the circumference. It's like angle at the center is twice the angle at the circumference, this thing, because arc AB subtends this angle at the center. What is this angle equal to? 180. And then the same arc subtends that angle at the circumference. So if that is 180, this is 90 degrees, because angle at the center 180 is twice the angle at the circumference, subtended by the same arc, right? But please people, this is not angle at the center is twice the angle at the circumference. It's simply angles in a semicircle. A diameter will subtend 90 at the circumference as long as the endpoints of the diameter form a closed triangle. Then that angle that they subtend at the circumference is 90 degrees. So we can say here angle C is 90 degrees. The reason angles in a semicircle. So I think the center theorems are clear for all of us, and we are clear about what center theorems we have. Line from center perpendicular to the chord, that's our acceptable reason when we use it. AM is equal to MB is the statement. Line from center to midpoint of a chord, the diagram, when we see it, will not have the 90 degrees there. So we say as a statement, OM is perpendicular to AB, and then the reason is line from center to midpoint of chord. Okay. Then we have angle at the center is two times angle at the circumference for 3 separate diagrams that we need to be aware of. And then last but not least, the last center theorem has to do with angles in a semicircle. The angle subtended at the circle or at the circumference by a diameter is a right angle. Okay, the 90 is usually not there. You just see a diameter, and so of course, as long as that diameter forms a closed triangle subtending an angle at the center with its endpoints subtending that angle with the closed triangle, then we say angle C is 90 degrees angles in semicircle. Guys, now we are going to move on and look at our tangent theorems. We have closed the case of our center theorems. So today we are going to jump into the tangent theorems. And we are going to take the tangent theorems, one tangent theorem at a time. So the first one that we are going to look at is the theorem that we refer to as the tangent chord theorem. Okay, let me just redraw this because I feel like it's not going to accomplish the purpose. So we're envisioning a circle, then there's a tangent that touches the circle at one point. Of course, that's what a tangent is, remember? It is external to the circle, but it touches it at one point. Then what we have internal is we have 3 chords. How many chords? 3. 1, 2, 3 chords. These chords, they form a triangle. Okay, now please take note that this tangent, it touches the circle at this point, thus forming an angle. The tangent and the chord form an angle here, but this is not the only angle that is formed between the tangent and the chord, there's another angle formed this side between the what? The tangent and the chord. So our theorem statement says, hi Muhle, how beautiful you are. The theorem statement says the angle between the tangent to a circle and the chord. I'm very well, Muhle, how are you? The angle between the tangent to a circle and the chord drawn from the point of contact. The angle between the tangent to a circle and the chord drawn from the point of contact. Guys, the angle, this angle between the tangent and the chord, this angle. So on this side we are talking about this angle, on this side we are talking about this angle. This is for grade 11, guys, specific to grade 11, foundational for grade 12. The angle between this tangent and that chord, the angle formed, all right, drawn from the point where the chord and the tangent meet, meaning at the point of contact. So this angle is equal to the angle in the alternate segment. Other wording that they usually use is equal to the angle subtended by the same chord. They either use is equal to the angle in the alternate segment, this is wording that they usually use, or they can say it is equal to the angle subtended by the same chord. Alright, Muhle, you should go follow me in my other TikTok page, the grade, that's where I do grade 8, 9 and 10 live lessons. Okay, so send me a DM if you can, send me a DM, or you can just go and search for Maths is a Game. The profile picture is a green profile picture. Okay, it just has a bit over 21,000 followers on TikTok. You just follow that page. That's where I do grade 8 and 9. So when I do grade 8 and 9, then you can just make sure you hit all the notifications that will make sure that you are alerted when I do go live on that page. And all grade 9 content and grade 8 content and grade 10 content I cover on that side fully. Okay, so check that one out. Anyways, so the angle subtended, guys, this chord here, which forms this angle with this tangent, this chord is directly subtending the angle here. This is the angle that is basically equal to that angle. Okay, so if we had A, B, C, let's say this was D and E, we could clearly say that angle BCD is equal to angle BAC. And our reason would be tan what? Tan chord theorem. BCD is equal to BAC. So the theorem says again, the angle between the tangent to a circle and the chord drawn from the point of contact is equal to the angle in the alternate segment, or we could say it is equal to the angle subtended by the same chord. So think about it. This chord, it's Maths is a Game as well. It's the same name, all right, but the profile picture is green instead of white. So this chord and this tangent form this angle, all right. But the very same chord subtends which angle at the circumference? It subtends the angle BAC. So that's why we say that angle BCD is equal to angle BAC. That is the Tangent theorem. Stated from the other side, there is another angle formed by this chord and this tangent. It is formed here at the point of contact. This chord subtends this angle at the circumference. So we say that this angle is equal to that one. So we can say then angle ACE is equal to angle ABC for the very same reason. Tangent theorem. Okay? Tangent theorem. So grade 11th, the Tangent theorem is simply that. Okay? There must be a tangent with a chord forming an angle. The angle formed there is equal to the angle that is subtended by the very same chord that forms the angle with the tangent. This chord subtends that angle. So we say angle ACE is equal to angle ABC. Reason? Tangent theorem. We can also say angle BCD, the angle formed by this chord and this tangent. That angle will be equal to the angle subtended by the same chord. BC subtends that angle at the circumference, so it means angle BCD is equal to angle BAC. The reason? Tangent theorem. So that is the Tangent theorem explained. The angle between the tangent to a circle and the chord drawn from the point of contact is equal to the angle in the alternate segment. Okay? Does that make sense? Or we can say is equal to the angle subtended by the same chord. Okay, so I hope that makes sense. Tangent theorem, great. Well, I'm glad, Mutle. Okay, awesome. All right, great. Well, we definitely, when I go live then for the grade 9s, and like I said, just DM me so that I can then also share with you what are the specifics for that grade. Okay. Thanks for being brave and commenting and asking your question. All right. Very persistent. I think you'll do well. That kind of attitude is the kind of attitude we need from the learners for them to do well. The next tangent theorem. Okay. Oh, let's just note here, guys. This is for this Tangent theorem is for when we have an acute angled triangle within our circle, but there are also cases where maybe it's for an obtuse angled triangle, all right, and we just need to take note of that. But I mean, we still have the angle formed by the tangent, and this chord will be equal to the angle in the alternate segment. Then you have this angle formed by this tangent and that chord, which will be equal to the angle in the alternate segment. Okay, I mean, it's tangent all the way, guys, tangent. Let's look at the second tangent theorem that we can have. If we have a tangent and we have a radius, okay, what we know here is that POP is perpendicular to PT. Okay, what's the reason? We say that a tangent is perpendicular to our radius. If this is a radius, that is a tangent. The relationship that exists between a radius and a tangent is that where they meet at 90 degrees. So we can say angle OPT is 90. We can also say angle OPS is 90 degrees. Okay, as long as we can clearly say that a tangent, we say a tangent to a circle is perpendicular to the radius at the point of contact. Okay, please guys, this is very different from this. Remember, this was a chord with a tangent. So a tangent and a chord basically form equal angles. There's an angle formed with the tangent and the chord on one side, and obviously that angle formed, all right, is equal to the angle that is subtended by that very same chord, as long as there's a triangle within that circle, and all three vertices must be at the circumference. Here we are saying if there's a radius, in other words, we can see a line from the center to the circumference, and then there is a tangent as well that meets that radius at the point of contact, then we can conclude that OP is truly perpendicular to PT, or we can say OP is truly perpendicular to SP. All right, and our reason is tan perpendicular to radius. This symbol, the upside down T, means perpendicular. All right, can I move on to the next theorem for tangents? Okay, we have the tan-chord theorem. Hopefully you can see the position of the angles that are equal for the tan-chord theorem. And then we have tangent perpendicular to radius, which means a tangent to a circle is always going to be perpendicular to its radius at the point of contact. And it's just as straightforward and as simple as that. Are we clear so far, guys? Are we clear about this? Can I move on to the next theorem for tangents? Because these are all theorems that have tangent in them. Okay, Zimpempe Mondliwa is saying yes, sir, you can move on. Okay, let's move on to the next theorem. The next theorem that has to do with our tangents is the theorem that says the theorems, okay, two tangents, let's say two tangents drawn from the same point. So this same point is this one. Okay, so just please don't mind this here. Zimpempe, you're in grade 10, but you're enjoying the life, so you are sticking around. It's fine. Me, I don't. Yeah. Okay. So this one is saying two tangents drawn to a circle. So if you have this tangent and then you have that tangent, they are drawn from the same point. This is the same point that these tangents are drawn from. Okay, two tangents drawn from the same point outside the circle are what? What is the conclusion we can make? They are equal in length. Two tangents this tangent and that tangent. The minute we say that those two tangents are drawn from the same point of contact, we can then conclude that those tangents are actually what? They are equal in length. They are equal in length. So let's say we have OP and we have ON. If these two tangents are drawn from the same point, we can conclude that OP is equal to ON. And the reason we use, guys, is basically tans from same point, or we can say tans from common point. So you choose which one flows more nicely with you. So two tangents drawn from the same point. What do we say about two tangents drawn from the same point, or from the same or common point? We say that two tangents drawn from the same point outside the circle are what? They are equal. Equal in what? In length. Two tangents. So we can clearly see that, we can clearly say ON is equal to OP. Reason, tangents from the same point. I hope we are clear there. Okay. Yeah, ish. Yeah, so these are the tangent theorems. They are the what? They are the tangent theorems. Tangent theorems. We are officially done with the tangent theorems. Please allow us to screenshot. So I'm going to screenshot, allow you to screenshot. There they are. That is the first ones, ne? The tan chord theorem, this one. Okay, tan chord, meaning the tangent chord, the relationship between the tangent and the chord. Okay, and the acceptable reason we use, both for an acute and an obtuse angle triangle. Then here we have the tangent perpendicular to the radius. Take note of the statement of the theorem. A tangent to a circle is perpendicular to the radius at the point of contact. Okay. Is it possible for one to be longer than the other? No. If they're saying, as they say, tangents from the same point, my guy. Okay. The theorem says tangents from the same point are equal in length. Okay. Then you have tangents drawn from the same point outside the circle are what? Are equal in length. Okay, let's take note of that. And the acceptable reason can either be tans from the same point or tans from common PT point for short. Okay, so those are our tangent theorems. So we've just dealt with the center theorems, and all of them are still fresh in our heads. Now we've just taken care of the tangent theorems. Anatima said these are the reasons that we use whenever we utilize. When you use tan chord theorem, that is the reason you use. Okay, if you are identifying an angle, right? Maybe they give you that this is 50, and you are identifying that BCD is equal to angle BAC. So if that is 50, that is also 50. The reason you would say is tan chord theorem. Tangent perpendicular to radius. The minute they ask you what is the value of the angle OPT, and then you say, oh, angle OPT is 90 degrees, and then the reason you will say tangent perpendicular to radius. Thank you for the rose. Sometimes this property of tangents from the same point outside the circle are equal in length is useful, okay, in situations maybe where they have, let's say, a circle, there are tangents that are drawn, let's say, for instance, then let's say, just say for some reason they have that, and maybe they give you, the lengths of the sides, and then basically when you can use the idea, oh no, tangents, if they are drawn from the same point, they are equal. So which would mean even from here to there we'd have equal, there from there they ought to be equal, and we could easily be able to find, if we know the side length on the side, we would definitely know that this side is equal to that side, and it would basically come from the idea of tangents from the same point. If let's say we have a chord that comes from those points of contact on the actual circumference, and we have a chord, so we have a triangle, and it would be an isosceles triangle, which means all the properties that relate to an isosceles triangle would be applicable, but it would come from the idea that the tangents from a common point are equal. Okay, so that we can either say tans from same point, or we can say tans from common point. Okay, so those are the tangent theorems in summary. Okay, now let's move to the next batch of clear explanation. I am so glad, Anat, so glad. Let's look at the next batch of theorems that we have. These are what I call the quadrilateral theorems. Quadrilateral. Okay. Quadrilateral. Theorem centered around cyclic quad. Let me say not quadrilateral, but cyclic quadrilateral theorems. Yeah, we call them the cyclic quadrilateral theorems. Let's just hold a sec here. It seems like someone has requested. Let's see what they have to say. Dark Beauty, what's happening? Dark Beauty, what's happening? Beauty of the Dark.
Iloni pure maths mostly. Yeah, pure maths.
Beauty of the Dark. I can't hear what you're saying. What's happening?
Are you doing pure maths, ne?
No, I'm not doing pure maths. I'm doing Euclidean geometry for grade 11.
Oh, it's geometry grade 11 in it. Oh, okay. Eh? Bye-bye. Bye-bye.
Bye-bye, Puma.
Bye.
Oh, okay. Okay, that is very interesting. Bye-bye, Puma. Bye-bye, Puma. Yeah, guys, if you request, remember, I don't occasionally take requests, but if I see maybe it seems like it's something pressing, I'll take your request. But hey, when I accept your request, please have something that obviously aligns with whatever you are listening to. You know, don't just randomly request. Bye bye, Pum. That's an interesting way to end that one. Anyways, let's proceed forth. The opposite angles of a cyclic quadrilateral are supplementary. I like how calm you are. It's fine. The opposite angles of a cyclic quadrilateral are supplementary. Now, a quadrilateral, guys, is a four-sided figure. Okay, four-sided figure. So whenever we have a quadrilateral whereby we can see all of the vertices, remember we did mention what a vertex is, and vertices just is a plural way of saying many vertex. So we say vertices for one word. So there is a vertex, vertex A, vertex B, vertex C, and vertex D. They form angles, of course. That's what a vertex does. Vertex is where two lines join, okay, or meet. So this A, B, C, D without the circle is a quadrilateral, but when all 4 points of a quadrilateral are on the circumference of the circle, we then call this a cyclic quadrilateral, or we say that A, B, C, and D are concyclic, which basically also underscores the idea of it being a cyclic quad. So then the theorem says the opposite angles of a cyclic quad are what? Are supplementary. The word supplementary means add up to 180 degrees. The opposite angles of a cyclic quad are what? Are supplementary. So which angles do we term here as being opposite angles? The opposite angles of a cyclic quad situated at the circumference of the circle. This would be an important point to make. The opposite angles of a cyclic quad situated at the circumference of the circle. All right, they must be situated, or they must be found at the circumference, these opposite angles. So which angles here would you say are the opposite angles of the cyclic quad? There are two pairs, not just one pair of opposite angles. So what are the pairs of opposite angles that we see in this diagram, guys? Can you give me the pairs of opposite angles, which you would then say are the opposite angles of the cyclic quad, which we refer to as being supplementary? Thank you, Anat. We have A and C. That organization and party that is ruling, or at least let me say is jointly ruling our country, A and C. Okay, so that would be A and C, that would be equal to 180 degrees. The reason that we use is op angles of cyclic quad. Op angles of cyclic quad. That's the short form of the reason that we use whenever we are saying angle A plus angle C is equal to 180 degrees. We say op angles of cyclic quad. So you guys said A and C, and yes, you guys are 100% correct. Silubonile, Felidi, and Flavorful Sense. You guys are 100% correct. We'd also say angle B plus angle D is equal to 180 degrees for the very same reason. Op angles of cyclic quad. That is the short form of our reason. So the opposite angles of a cyclic quad are supplementary. Okay, that's one of our cyclic quadrilateral theorems. Two. One, voila, voila, voila. Yes, this theorem says the exterior angle of a cyclic quad is equal to the interior opposite angle. Let's relook at this again. The exterior angle of a cyclic quad is equal to the interior opposite angle. So let's look at this diagram that we have right here. The exterior angle. I want to just emphasize something here, guys, that this exterior angle that they are talking about, if you look at A, B, C, D, it's an obvious quadrilateral, which is a cyclic quad. That is one of the conditions that need to be in place for this exterior angle to then be identified, and we need to identify it as per what we understand the exterior angle to be. So if you look at BC, BC has an extension which is E, and so the line BCE is in the same horizontal plane, and therefore because it is in the same line as the side of the quadrilateral, we call DCE to be the exterior angle, or ECD is the exterior angle. Angle DCE is the exterior angle. We can say angle ECD is the exterior angle. Guys, the exterior angle must be in line with the side of the quadrilateral in order to qualify as the true exterior. So all in all, what I'm saying is that if you have a quad like this, and then you have an exterior that's like that, this is not a true exterior. This is not a true exterior because it is not in line with the side of the quadrilateral. Any exterior that you have must be in line with a side of the quadrilateral. The quadrilateral you are referring to, okay, must be in line with the extension of the side, which basically leads you to the exterior angle. So this exterior angle is not a true exterior angle that is equal to the interior opposite angle, but this one is, because it is in line with the side BC. CE is simply an extension of BC, so the side must be in line with the extension that forms the exterior angle. That's what qualifies this as a true exterior angle. So we can then say, as somebody said in the comment section, angle DCE is equal to angle A, because this angle is the exterior angle, and therefore this angle A is the interior opposite angle. Okay, I hope it makes sense, guys. BTK 4K, I don't understand what in the world you are typing there. DBE plus DC is equal to 180. That is 100% wrong. I don't know what you are saying there. Makes no sense. DCE, you are saying DCE. I mean DBE, sorry, is plus DCE. My guy. I don't know, like, what that is, like some serious confusion there. Sure, that is serious confusion. I don't know what you're typing there. Let's see, what is this? Let's see, DBE plus DCE. No, 100% wrong. DBE plus DCE is not 180. DCE plus DCB, yes, DCE plus DCB is definitely equal to 180 angles on a straight line. But yeah, but remember, we are not on that right now. Right now, we are just simply trying to explain the idea of the exterior angle of a cyclic quad is equal to the interior opposite angle. The exterior is this one. It is the exterior angle. The word exterior means outside angle. But to further explain that outside angle, it must be an outside angle formed in line with the side of the quadrilateral. That's why I'm saying in line with BC, CE is an extension in the same line. So this is a true exterior angle. But this here, all right, if you look at this side, it's not truly in line. It's not like in the same straight line. So therefore, this here does not form the true exterior angle because it's not in line with the side of the quadrilateral. So always check those things because there's true exteriors and there's false exteriors. So this is a true exterior angle because CE is an extension of BC in the same straight line. So it's a true exterior. So we can say angle DCE, which is the exterior angle, is equal to the interior opposite angle, which means it's equal to angle A. All right. Let's say we had something like this as well. An extension of AB to F in the same line, right? Okay, what would be the exterior angle for what you see here, and which angle would it be equal to? What would be the exterior angle for what we have extended to F, and then what would that angle be equal to? CBF. Yes, BTK. CBF, angle CBF, which is equal to angle D. Okay, way to go, BTK. I think now we are in the same page, my guy. CBF, or you can say angle FBC. It's no different. But though that angle would be equal to angle D. Yes, Anat. 100% spot on. All right. So this would be the true exterior angle. Yes, we understand that there's a cap on top of the angle. I think they do understand that, but it's just that they are trying to just make sure they get the notation or the identification of the angle, at least first and foremost. So the exterior angle would be angle CBF. That would be equal to the interior opposite angle, which you guys are spot on by saying is angle D. So it's like saying CBF is equal to angle D. And remember, guys, our reason is X angle of cyclic quad. X angle of cyclic quad. Okay, that is the acceptable reason you write down whenever you're using that. Okay. 3. There's Anati Massetti's famous one, the one Anati asked me about. Anati, do you know which next diagram I'm going to draw here? Because it was that diagram you asked me about yesterday. You still remember your question about the bow tie for angle at the center is twice the angle at the circumference compared to the bow tie for this one. Okay, this bow tie compared to the bow tie of angle at the center is twice the angle at the circumference. Okay, hopefully now you note the difference and you note it very well. Okay, what does that say? angle subtended by, now AB can either be called a arc, but if we join A and B, we have a chord. All right, so the arc subtends angle D, the same arc subtends angle C. So for this particular one, we say angle D is equal to angle C, and the reason we say that is angles in same seg. Okay, not only is angle D equal to angle C, but angle A is equal to angle B as well. It's because this arc CD subtends this angle A and it subtends this angle B. So we say angles in same seg, guys. That's how we write it in short. Angles in the same seg. Simple as that. Okay, you don't have to write R equal, just angles in the same seg. Okay, so you state the equal angles and you state the reason why you are saying those angles are equal. Okay, angle C is equal to angle D, angles in the same seg. Angle A is equal to angle B, angles in the same seg. Okay, then from here, from the quadrilaterals, okay, we have something that comes out from angles in the same seg, which we call the equal chords corollaries. The equal chords corollaries. Okay, so you're gonna duly note the equal chords corollaries. Okay, now as some of you are asking me, what in the world are you talking about now? Say corollary. Okay, what is the meaning of corollaries in maths? Okay, a corollary is simply like a statement. Okay, it's a statement that follows directly from a already proven theorem or axiom. It is a what? It is a statement or a proposition that follows directly from an already proven theorem or statement. I'm going to show you the corollaries that I'm talking about. So coming from the angles in the same segment theorem, there are these corollaries that we can deduce from the angles in the same segment. The first one says equal chords subtend equal angles at the circumference of the circle. Okay. Equal chords. Here is the chords. You see this triangle? You see this triangle? It's like they are identical or congruent, if you want to call it that. So this chord and that chord, because they are equal in length, they both subtend the same angle at the circumference. Okay, equal chords, equal angles. Okay, equal chords, equal angles. All right, this is the reason. Okay, these triangles could be triangles that also maybe within, just want to show you something here, within, okay, let's just say that is a chord. Okay, let me just redraw this. Let's say that's a circle, say that's a chord, say that's a chord. So we go on like this, and then let's say maybe we go on like that. And let's say the chords are equal. So if the chords are equal, then we say equal chords subtend what? Equal angles at the circumference. So as long as the chords are equal for these two respective triangles, we say that if the triangles actually touch the circumference of the circle, both of those triangles do so, then the chords are equal. We say that equal chords equal angles. Okay. So for instance, let's say they had written 50 degrees and then they write x here. And they like find the value of x. So I would say if that is 50, obviously I would say x is equal to 50 degrees, and when I write my reason, okay, x is equal to 50 degrees reason, equal chords, equal angles. Okay, straightforward like that. Equal chords, equal angles. No confusion, straightforward, no misconception about it. Okay, so that is the first corollary that comes from angles in the same segment. It is equal chords, equal angles. Let's look at this one. There's another one. Equal chords subtend equal angles at the center. Equal chords subtend equal angles at the circumference. So it's the same thing, right? Here we wouldn't say this angle is equal to that one because of vertically opposite angles. No, we say that angle is equal to that one. Why? Because equal chords subtend equal angles at the center. So this here we can also say equal chords equal angles, or we can say equal, as in like the word equal, chords equal angles. Okay, then the very last corollary says equal chords in equal circles subtend equal angles. So let's say these circles are the exact same size, then the triangles inside, you have a particular chord where the chords for the different circles are actually equal. Then we say those chords individually, because they are within circles that are equal, those chords will subtend the very same angle in the circumference of each circle. All right. So in other words, these circles are separate, but as separate as they are, if you learn that both of these circles are actually equal circles, then you can say that if they are equal circles and each chord for both of these triangles in those circles is also equal, then we say those chords that are equal will subtend the same angle, the same identical angle in the circumference. No, these are not the grade 12s, guys. These are corollaries or statements that come from angles in the same segment, and they are not grade 12s. They are all under grade 11. And let me tell you this, they are so many times incorporated into your actual problems that if you don't know them, you may actually find yourself not being able to actually get the marks that you need to get. So if you guys, it's your first time, okay, if it's your first time hearing this, then I don't know why you guys are not pumping it in with lighting up my gift gallery. because it means I am actually genuinely helping you guys. Like, I mean, this is not just, I mean, I am genuinely, honestly exposing some of you to things that you've never in your lives heard, even from your own educators. It's not, this is not like something that, like, I mean, I don't know about you guys, but like, if let's say you had like maybe asked someone to come and tutor you, I would understand that you would basically go to that person with the intention that they would actually, you know, do justice to you and deliver content that is appropriate for you. But literally, I am coming on this live free of charge, right? I'm not really expecting anything from any of you guys, right? But it's nice when you do gift. I'm not gonna lie to you. But then you guys are shocked that, sir, is this grade 12? And I'm like, guys, this is not grade 12. Okay, you have your main theorems, which are the theorems that we've covered, whereby I have actually done you the favor of grouping the center theorem so that in your head you have a good idea what are the center theorems. I have grouped the tangent theorems for you. Then I grouped the quadrilaterals for you. Now all I'm doing is I'm taking that angles in the same segment, angles subtended by a chord of the circle on the same side of the chord are equal. I'm taking that theorem and I am saying to you, there are 3 corollaries. What is a corollary? A corollary is a proposition. It is a theorem or statement that follows directly and easily from an already proven theorem, and it requires little or no additional proof. So I don't need to prove this. It is derived from angles in the same segment. So we talk about equal chords that subtend equal angles at the circumference. And this is basically, you know, used in that sense. We talk about equal chords subtending equal angles where? At the center of the circle. We talk about equal chords. There's the equal chords inside of equal circles. And if those chords are inside equal circles, then we say that those chords actually subtend equal angles at the circumference. So if I know that these 2 circles have the same size, and I'm told that the chords are equal, then it means that the angles there that you will find will be exactly identical. They are the same as well. Okay. So what did we say? What do we say here when we use this reason? We say equal chords, equal circles, equal angles. Just those 3 things. Equal chords, equal circles, equal angle. You write those 3. That is basically your reasoning. Whenever you are now going to say, if this is 50 and I write x there, then you say x is equal to 50 degrees. Then I ask you the reason. You say equal chords, equal circles, equal angles. It's as straightforward as that. Nothing more, nothing less. Thank you so much, guys. By the way, let me thank you heartily. Really appreciate this. I'm not taking for granted. BTK 4K, thank you, guys, for the rose. 5 roses, I really appreciate them. Anati Maseta, really appreciate 2, 3 roses, and then the additional 6 as well. After you gave the 6, you gave the 5. Thank you so much, BTK4. I really appreciate you, guys. And also Anati. Gyalebocha. Gyalebocha, guys. Gyalebocha. Gyalebocha. All right. Okay. So there we have it, guys. Equal chords, equal angles. We have equal chords, equal angles as well. But this one is talking about the equal chords subtending equal angles at the center. This one, equal circles, equal chords, equal angles. Okay, so that is the extension of what? Of the corollary coming from angles in the same segment, the theorem of angles in the same segment. Okay, I hope it makes sense, guys. And yeah, that is basically what we have to offer for you beautiful people. All right, now I want to touch on the last thing that pertains to the theorems. Okay, and this has to do with proving certain things. Sometimes you are asked to prove that something is a cyclic quad. I want us guys to also step into this, proving that something is a cyclic quad. How do you prove that something is a cyclic quad? And this is what I want to talk to. All right, I want to talk to this. Okay, so there are 3 possible avenues that you look at when you want to prove that something is a cyclic quad. All right, we first looked at the cyclic quad theorems, but the minute we want to prove that something is a cyclic quad, we basically use the converse of these theorems that basically are under what? That are under the cyclic quad. So here's what I mean. So in other words, if you are given a diagram, let's say it's a quadrilateral like this, and then they give you here 50 degrees, and then they give you here 130 degrees. That is A, B, C, and D. I'm just saying, guys. And then they say, prove A, B, C, D is a cyclic quad. All right. When now you look at the diagram and you see, hey, angle A is 50 and angle D is 130. All right. So when you see that angle A is 50 degrees, into is given to you, angle D is 130 degrees, and 2 is also given to you. All right. Then you can see, man, that A plus D is angle A plus D is 50 plus 130 degrees, which is 180 degrees. Right. Then you basically conclude that ABCD is a cyclic quad. Now, there's an important reason you need to give. And the important reason you need to give is something that someone, did someone say it? No, nobody said it. Okay. No, not opposite angles of cyclic quad. No, remember, this is not a cyclic quad yet. You want to prove that it is a cyclic quad. Okay. Yeah, so we can't say opposite angles of a cyclic quad. We can't say interior angles add up to 360. You guys are not getting it. We can't say all of that. You can't say all of that. Okay, so I need someone to, I'm going to wait for someone to tell me what I want to hear. No. Reason doesn't have to do with chords at all. I'm wanting specific wording. You guys are saying opposite angles of a cyclic quad. I'm not happy with that. You know, we identified angle A, which is 50 degrees, which is given. We identified angle D, which is 130 degrees, that is given. Then we saw about angle A plus angle D is 180 degrees. 50 plus 130 is 180. Then we are concluded that triangle, that ABCD is a cyclic quad. What is the reason? Why can we say that it is a cyclic quad? Thank you, Resima Nobela. Please take note of Resima's. Thank you, Resima. What did we just identify? Angle A, angle D. In a what? What is this? This is a quadrilateral. So we say ABCD is a cyclic quad. The reason, which is very critical, that we write correctly, we must write it correctly, all right? And as I write it correctly, I just want to show you, because I don't want to speak things that are, I don't want to speak things. Okay, here is this thing here, guys. Right, this is the exam guideline, the acceptable reason document. The statement here says, if the opposite angles of a what, guys? What is this word? The opposite angles of a, if the opposite angles of a quadrilateral are supplementary, then the quadrilateral can be mentioned to be cyclic. The quadrilateral then is cyclic. Go to the reason. Okay. If the opposite angles of a quadrilateral are supplementary, then the quadrilateral is cyclic. Look at the acceptable reason. We can either say opposite angles of quad sub, opposite angles, angles quad sub, or they are saying, we can say converse angles of cyclic quad. Guys, this is not coming from me. This is from the acceptable reason document, which is from the Department of Basic Education. Okay, so I'm not writing this myself. This is coming from the document. So this is one of the ways in which we prove that a quadrilateral is a cyclic quad. If we can identify in a given quadrilateral opposite angles, which when we add together, we find that they add up to 180. It means we have just seen a quadrilateral that has angles that are supplementary. So then we can conclude and say ABCD is a cyclic quad. Why? Op angles quad sub. Okay, or we can say converse of op angles of a cyclic quad, where now you must choose the one that you feel you are most comfortable with. So when in any event where you prove that the opposite angles of a quadrilateral, they add up to 180, and you conclude that ABCD is a cyclic quad, this is your reasoning. This or that would be fine. Okay, let's look at the next case. So this is case 1, proving that something is a cyclic quad. You can either prove that the opposite angles of a particular quadrilateral are supplementary. Okay, that gives you grounds to say that that particular quadrilateral is in actual fact a cyclic quad. Let's look at the next situation. Once again, what do we have here? What do we have here? Let's say M N O P Q. let's say this is 60, and that is x, that is 120. Okay, now of course we could see that, okay, opposite angles are supplementary, and then conclude that's a cyclic quad. Let's try and venture and just try and use a different way to prove that this is a cyclic quad. There's the option of opposite angles of a quadrilateral, but also there's the option of proving that this is a cyclic quad in another way. All right, so this x, we can say x plus 60 degrees is equal to 180. Reason angles on a straight line. Then means we can find that external angle x is equal to 180 minus 60, so x is equal to 120. Okay, so I know x is 120. I then compare the angle outside, which is in line, because you see this angle, though it is outside, it is in line with the side of NO. So Q extends and then x is 120. You can see that this exterior angle of the quadrilateral is equal to the interior opposite angle. So can we say prove, if they are say prove that MNOP is a cyclic quad, can we prove that it is? Yes. Well, angle M is equal to angle POQ, which are both 120 degrees. Therefore, we can say MNOP is a cyclic quad. What's the reason for saying MNOP is a cyclic quad? Exterior angles of quad are equal. Now let's be careful with this one, guys. We want to be writing the one thing that will be 100% correct. Let's come here. If the exterior angle of a quadrilateral, you see they are talking about a quadrilateral. A quadrilateral is just a simple four-sided shape. They are saying if the exterior angle, not of a cyclic quad, but if the exterior angle of a what? Of a four-sided shape quadrilateral is equal to the interior opposite angle of the quadrilateral, then the quadrilateral is cyclic. Let's look at the acceptable reason that they write here. Look at this. Ext angle equal int op angle. Ext angle equal int op angle. Or you can say converse of exterior angle of cyclic quad. So you can say ext angle equal to int op angle. Or if you feel that that will basically waste your time, guys, converse. Do you see now we are using this converse idea the second time? The first time for the opposite angles of a quadrilateral, we could say converse op angles of cyclic quad. Now again, for the exterior angle, we can say converse exterior angle of cyclic quad. As long as we don't say exterior angle of cyclic quad. No, we say converse. This is the opposite. All right. So for proving that it is a quadrilateral, we can go the direction of just adding the word converse before saying converse opposite angles of cyclic quad if we are dealing with this situation. Or we could say converse exterior angle of cyclic quad. So let's decide, guys, which one as individuals we are going to stick to and flow with. All right, please, guys, because the reasoning is here for us to use. Okay, and remember remember, in the exam centers, when they mark, they are consulting the exam guideline for the most accurate and common reasons that learners can use. All right? Yeah. All right. Now let's move. The third one. Yeah. It's up to you, my guys. It's up to you which one you use. I see people let's it's up to you which one you want to use. Okay? Yeah, it's up to you. It's up to you. It's up to you. The third case, all right, has to do with bow tie. Okay, has to do with our bow tie. Has to do with our bow tie. So they're asking you, is this a cyclic quad? Okay, but of course, if this is 30 and that is 30, what can we then say, guys? Okay, let's say that is A, that is B, that is C, that is D. You can see that is 30, we can see that is 30. They're saying prove that A, B, C, D is a cyclic quad. Okay, so of course, okay, we see angle A is equal to angle B, which is 30 degrees. We see the position of the angles in that place. Therefore, A, B, C, D is a cyclic quad. But let's be very careful in our reasoning. We can't say angles in the same segment. Remember, there's no circle around this. So saying it is a cyclic quad, the reason for that is converse angles in same seg. Converse angles in same seg. And I'm going to show you, so that you guys, you see, you don't think I'm not making things up. Yeah, or you can say line subtends equal angles. That's another thing you could say. Line subtends equal angles. Jonga, let's see. If a line segment joining 2 points subtends equal angles at 2 points, oh no, what's happening now? 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 What is happening now? Okay, here we are. Let's get back to this. Okay. If a line segment joining 2 points subtends equal angles at 2 points on the same side of the line segment, then the four points are concyclic. This is what it's speaking to. You can either say line subtends equal angles, or you can say converse angles in the same seg. Angles in the same seg. So it seems like the converse thing can work beautifully. All right, I think for all three cases, we can either say converse opposite angles of a cyclic quad, that works nicely, or we can say converse exterior angle of cyclic quad, or we can say converse angles in the same seg. Okay, so it is this converse idea, I think, that can actually just make life easy for all three cases. This one, easily, we prove ABCD is a cyclic quad, reason converse, okay, opposite angles of cyclic quad. We prove that this thing is a cyclic quad because of exterior angle is equal to interior opposite angle, so we just say converse of exterior angle of cyclic quad. converse exterior angle of cyclic quad. We prove that indeed that the angles that are subtended on the same side are equal. Then we just say converse angles in the same segment. Okay, so yeah, converse, guys, I think works wonders. Okay, converse, converse, converse. So let's stick to converse. Okay, let's stick to converse. Let us stick to that one because I think it just nicely summarizes. Because converse means the opposite of the actual theorem, which is basically what we want. Okay, yes, it is. Because anyways, when we are using this in an actual cyclic quad, where this is 50, and we want to say this is 50, and we are given x, and we say x is equal to c, which is 130 degrees. The reason we give is opposite angles of a cyclic quad. Okay, so we know that if we are proving, okay, when we are proving, then we say converse of angles in the same seg. Okay, Tsebiso Mafefe, that is emotional blackmail. You, mister, you never care about us metrics. Look at this guy. Tsebiso Mafefe, you are emotionally blackmailing me, you. Certainly, though, certainly, emotionally blackmailing me, wanting to make me feel bad about not caring about you. The interesting thing is me actually explaining this, all right, for grade 11 specifically, is caring a lot about grade 12s, okay, the Euclidean geometry, because 75 or even more than 75% of the work that you guys cover in grade 12 is mostly your grade 11 and grade 10. And I spent the past few days doing basics in grade 8 and 9 with geometry, doing now circle geometry for grade 11. So I think if you were to actually look at this, I care very much about the grade 12s. And you know what? If you join my grade 8 and my grade 9 live lessons, you will in actual fact appreciate the basics that you are being reminded yourself as you join those grade 8 and 9 lessons. Okay, so all in all, my guy, I think I care very much about grades. I've watched all your videos on YouTube. You are funny. It's a piece of my favorite. All of them. To say all, though, I wouldn't say it quantifies everything. My soul. But anyways, yeah, I think Anati, you are 100% correct. I've been all about the grade 12s this past few days, to be honest, and I've been dropping some nuggets like crazy. So hopefully gets up. So if you've missed my live lessons the past few days, you can catch up. You are the one that's watching all my YouTube videos. I'm going to upload, all right? And you must have seen that I have a playlist now for Euclidean geometry basics for 2026, okay? Don't mind, I do have a grade 11 geometry. Actually, I've done lessons on geometry for grade 11 in the past, right? Where I've gone through everything. But now I'm building up, and I'm going to get into the riders and proving and all of that stuff. We're going to get into problems shortly, but then in the next few days, I'll be getting into the grade 12 geometry, and we'll be diving deep into that, your proportionality theorem, similarity, Pythagorean or Pythagoras, and so forth. So don't worry. Okay. Yes, Kaziti. This is being recorded most by TikTok. So what I do is I save the video and I upload it. Okay. I upload it there in the YouTube channel. YouTube handle, there guys, the link is in my bio. Can't you guys are not even here. I often say this, Jay. the link is in my bio. Okay, and sometimes I do live lessons on the YouTube channel, because it makes for easier saving the video, because immediately after I do the live lesson on YouTube, it just saves the lesson on there. And I mostly do YouTube live lessons like literally in the morning before I go to work. So yeah, and I primarily do focus, yes, on some grade 10 aspects, some grade 11 aspects. So for instance, trigonometry, I've been focusing on the grade 10 and the grade 11 aspects of trigonometry. There's a playlist that literally is just from the YouTube live lessons. It's not even from TikTok, it's from YouTube live lessons that I've done on YouTube. All right. So you can check those out in your own time. If you just want to get the basics out of the way in grade 10 and grade 11, you can actually do that. At what time do I do the live lessons on YouTube? In the mornings. Yo guys, yeah, I do them literally 5 a.m. in the morning, 5 a.m. up until like 6 past 6, 7. Yeah, it just depends on a good day. But like I said, I'm just trying to also cover the grade 10s, so I've been finishing up the grade 10 trigonometry. I've just done the grade 10 trigonometry. Okay, grade 10 trigonometry. Just recently I did the Pythagoras type problems on the Cartesian plane, how you sketch and draw a diagram on the Cartesian plane and use that to basically find trigonometric expressions. I was doing that just not so long ago, and also just trying to help the grade 10s as well to get a bit confident with their work. This also helps my personal learners that I have, like my learners at my school, but it then also helps those learners that are actually here in Maths is a Game that need sort of like the support above and beyond what they are getting at school. But what is making me sad, I had a learner that was crying in grade 11 that was saying he was doing some of the things the way that I have been explaining in the live lessons. They are 100% correct and they are accurate, but then the teacher is marking them wrong because they are not doing things the way that the teacher basically has taught. And it's more of like the methods, some of them which are basically easy, they make life easy for the learner. So I was a bit sad about that. So it's actually sad when that does happen, because maybe the method is not comprehended or understood in certain cases, and I'm like, but yeah, this is a common way. Because remember guys, I actually mark papers. Okay, I mark papers at the end of the year for grade 12. So I go like the exam centers, the marking centers, and all of that stuff. So there's a little bit more experience that is not just informed by teaching in a school or teaching or tutoring, but it is informed by the experience that I've had in marking at exam centers when learners in grade 12 write at the end of the year. So many of the things I share, or which I give you guys as advice, is not just like run of the mill advice. It's actually legit, genuine, informed by the experience I've had marking at exam centers at the end of the year. And yeah, unfortunately we don't all have that privilege, and therefore some people, they miss out on certain things, and when they do, there's certain things that they don't know about. Yeah, but nonetheless, let's stop that ranting and explanation. Let's continue. Okay. Hygiene schools in grade 12, teachers are marking everything wrong of mine wrong. Yeah, I think you then need to take it the extra mile, BTK, and sort of like go to the teacher when you do something, and just go and ask them to check and verify if whether the way that you've done something is correct. Because some teachers need to just have they just need to be made aware of maybe alternative ways. I mean, this is what we do at exam marking centers. If you're at an exam marking center and it so happens that I come across a question and the way that a learner has answered something, if I'm not familiar with it, then it is my prerogative to ask, other experienced teachers or other teachers if they are aware of something like this. Then have a discussion around the approach and the attempt of a particular learner, and then come to a consensus as to whether this way is credible and feasible, and if marks can be awarded. It's so sad when learners are going to be losing marks simply because people lack just they lack perceiving what is in front of them and seeing that it is actually mathematically correct. So yeah, that's making me really sad, because now it makes even tutoring learners for me a futile exercise, because, I mean, yeah, you give learners help, and then the next thing, their teachers mark them wrong at their schools. Aye. So hence I'm saying maybe it becomes important. Then just go back to your teacher and ask, of the method, is this correct? And maybe find a way, creative, smart way to basically sensitize your teachers to other methods and other ways of basically approaching certain problems. And maybe they may learn something if they possess humility, Hey, yeah. Anyways, okay, let's hold that. So guys, these are the 3 ways in which we can prove that a quadrilateral is actually cyclic. Okay, and you saw from the document. Okay, yo, BTK, that's hectic. Ish. Yikes. Okay. I think we've done prove also. Proving, remember, besides proving that something is a cyclic quad, you may also be asked to prove that a particular line is a tangent. So how do you prove that a line is a tangent? So I need to also make us aware of this too, because okay, prove that a line is a tangent. Also, not only that, prove that a line is a diameter. Okay, there's certain cases where you're asked to prove that a line is a diameter. Okay, so these are things you need to be aware of. You see now, equal chords. Okay, so proving that a line is a tangent. Just wanna check this out quickly. Tangent perpendicular to diameter. Converse of tangent perpendicular to diameter. Look at this. If a line is drawn perpendicular to a radius or diameter at the point where the radius or diameter meets the circle, then the line is a tangent to the circle. I repeat, if a line is drawn perpendicular to a radius or a diameter at the point where the radius or diameter meets the circle, then the line is a tangent to the circle. So there's converse of tangent perpendicular to radius or converse of tangent perpendicular to the diameter. One of two. Converse of tangent perpendicular to a radius, converse of tangent perpendicular to a diameter. Okay, that's one way. That's one way. Let's look at another. There's this one. If a line is drawn through the endpoint of a chord, making with the chord an angle equal to the angle in the alternate segment, then the line is a tangent to the circle. Repeat. If a line is drawn through the endpoint of a chord, making with the chord an angle equal to an angle in the alternate segment, then the line is a tangent to the circle. This is converse of tan-chord theorem. Converse of tan-chord theorem, or we say angle between line and chord. Okay, you are trying to prove that a line is a tangent. You can use converse of tan-chord theorem. So there are two so far: converse of tan-chord theorem, converse of tangent perpendicular to radius, or converse of tangent perpendicular to diameter. So these are two possible ways to prove that a tangent, a line, is actually a tangent. So I wanted you to note that. Then lastly, how to prove that a line is a diameter? That would be the converse of angles in a semicircle. So let's look at this. If the angle subtended by the chord at the circumference of the circle is 90 degrees, then that particular chord is not just an ordinary chord, but it is a diameter. I repeat again. If the angle subtended by the chord at the circumference of the circle is 90 degrees, then the chord is a diameter. Okay? So, all in all, to prove that a line is a tangent, you have 1 converse of tan chord, 2 converse tan perpendicular to radius, or better yet, converse of tan perpendicular to diameter. So tan chord and converse of tan chord and converse of tan perpendicular to radius. Proving that a line is a diameter, you have converse angles in semicircle. Okay. So a particular chord, if that chord subtends 90 at the circumference, then it means that chord is not just an ordinary chord, but it is a diameter. Okay, which is why that chord basically makes up the semicircle. All right. So yeah, guys, I just want you to know these so well. Okay, let's check the order here. You see, remember that corollary, which I said is equal chords in equal circles subtends equal angles at the circumference. It actually starts with equal circles, equal chords, equal angles. So it must be the circles first that are equal, followed by the equal chord, followed by the equal circles. You can see that these are all separated. Equal circles separated by a semicolon, equal chords, then another semicolon, then equal angles. Okay, please take note. Then there's the other corollary. Equal chords subtend equal angles at the center of the circle, equal chords, equal angles, and then the equal chords subtend equal angles at the circumference of the circle, equal chords, equal angles. So the reasoning here for both equal chords subtending equal angles at the circumference and equal chords subtending equal angles at the center, the reasons are the same. This one just adds equal circles because it's equal circles, equal chords, equal angles. Okay, the corollaries are there, guys. You see? Equal chords in equal circles. So there's also equal chords in equal circles subtending equal angles at the center of the circles. So you have two separate circles. They are the same. Okay. So if you don't write your reason like that, they are wrong. Yeah, we try to, as far as possible, align it with the acceptable reason document. Okay. Let me just read here the disclaimer here. Acceptable reasons, Euclidean geometry. It says, in order to have some kind of uniformity, the use of the following shortened versions of the theorem statements is encouraged. This is coming from the exam guideline. So in order to have some kind of uniformity, the use of the following shortened versions of the theorem statements is encouraged. Okay. Yeah, so these reasons are there for lines, for triangles, for your circles. All of the circles theorems are there. Okay, you can see them, many of them. Your quadrilaterals, okay, yeah, your rhombus, parallelogram. You can see, guys, diagonals. You see, so there's all of these, right? So this is a must document to be up there on your wall. Okay, yeah, okay, it's a must that this document be up there. Yeah, I think, guys, we have basically touched on all that we need to touch on for tonight. That is how that after you have all of this touched, that's when you need to be someone that says, okay, let's go and grab a few problems so that we can do them. All right, I think I'm going to just allow us to do this one for tonight, okay, and then I'm going to call it a night. Let's look at this particular one, all right, just so that we can have another minimal start. Tomorrow I will jump into more problems, guys, because at least now we have our tools. Okay, so I call the theorems our tools. Once we have a good idea how to use a spade, how to use a fork and knife, how to use a lawnmower and so forth, the minute you know your tools and you know how to use them, then it's easy to be able to use them and use them well. So in the given diagram, let's look at this. A, B, C, and D, and E. Here we go. A, B, C, D, and E are points on the circle. A, B, C, D, and E. They are all points on the circle. Look at A, B, for instance, and D, E. They are all points on the circumference of the circle, and it's 1, 2, 3, 4 points. Cyclic quad stuff. Look at B, C, D, E. Four-sided. Cyclic quad stuff. Look at A, C, D, E. All points on the circumference. Cyclic quad stuff. I mean, what more? Okay. So anyways, we are told that BE is a diameter. BE, we are told, is a diameter. Ooh, diameter. Immediately in our heads, we're like, center theorem. BD is produced. BD, look at that. It is produced. So that means we have an outside angle for DEAB. We have an exterior angle, and it's a true exterior angle because BD extended to DF. It's in the same horizontal line. BD is produced, and it meets what? It meets AE at F. Right. E3, where's E3? It's 62 degrees. It's labeled. B1, 50 degrees. It's also labeled. So we have that all there. Determine with reasons. Obey, baby. Oh my, look at this. Yeah, they are saying we must determine before anyone else. Ooh, before anyone else. Obey. Before anyone else. Obey. Okay. BAE. They want me to determine BAE. And they need me to determine that with the reasons. So guys, what is angle BAE? And why? Ontatile in the comment section had said BAE is equal to 9. 9 with a included bracket and then the degrees. BAE, not BAR, Gazi. Be careful. BAE. So Gazi is saying BAR is 90. Anat is saying it's 90. Okay. Gazi 90, not BAR, BAE, my guy. 130 90. Oh, you meant to say 90 degrees. So BAE is 90 degrees, angles from semicircle. Remember, guys, it's not angles from circles, angles in a semicircle. BAE. We were told most that BE is a diameter. So if BE is a diameter, that means this entire angle, all of it, 90. So we're going to say BAE is equal to 90 degrees. And reason, angles in semicircle. Acceptable reason. 1 mark for statement. One mark for reason. Or it could be just 1 mark for both statement and reason. We always can be aware of that. The minute you get something and it's 100% correct, you can go and update your diagram. Let's move to the next one. Angle E1. Ooh, guys, angle E1. What are your thoughts? Angle E1. What do you see? Where is angle E1? There is angle E1. Okay. Ooh, BTK. 4K. Angle E is 30 degrees. Angles in a triangle. Okay, be careful now. We want to employ the acceptable reason, not just to be careless and say angles in a triangle. Angles in a triangle is not complete. It's not a complete true theorem support. Angle A plus angle E1, yes, plus angle B1. Okay, very true. So this is a triangle BAE. Angle A plus angle E plus angle B1. So that's 50. Okay, sum of angles in a triangle. Okay, so you guys, I think we got it there. So it's always nice to identify the triangle you are working with in triangle ABF. Okay, angle B1 plus angle A plus angle E1 equal to 180 degrees. What's the reason? Sum of angles in the triangle. Yes, we can say sum of angles in triangle, or we can say angle sum in triangle, or we can say interior angles triangle. Okay, angle B1 give 15, A give 90, E1 don't know, 180 degrees. Transpose 180 minus 50 minus what is it? 50, yeah, 50 plus 90 minus 140. Angle E1 is equal to 40 degrees. That's angle E1. Okay, angle BAE 90 degrees. Angle E1, it's 40 degrees. Okay, guys, I'm a bit tired now. All right, maybe let's just finish this off. Okay, it's nearly done. At least that's question 3. Okay, angle E1 is 40 degrees, right? So what you do when you get something, update, right? Let's continue. We want angle C1. Where's angle C1? Angle C1 is here. Okay, C1 has a relationship with angle E1. Do you see that? C1 has a relationship with E1 because angle arc AB or chord AB subtends angle C1 and it also subtends angle E1. So we can say angle E1 is equal to angle C1. If you don't see it, take your diagram. You can always twist it around like this. Okay, C1, here is C1. E1, arc AB, E1 and C1. So these two angles, C1 and E1, are both equal to 40 degrees. What's the reason? Angle E1 is equal to angle C1, which is equal to 40 degrees. Angles in same seg. I looked at it differently. Tell me, how did you look at it? What did you see? What's the reason? C1. I need you to tell me, what did you see? You looked at it differently, but I get the same answer. How did you look at it? Angle C1. E1. Okay, let's just check. E1 plus E2. Be careful, be careful. Angle E1 plus angle E2 is giving you 180. How? E1 plus E2 is equal to 180 in no ways. Because E2 is formed by DEB. Guys, I said angle E1 is equal to angle C1. Let's go here. Where's E1? There is E1. It's this angle right there. Where is C1? Here is C1. This angle right there. You see this chord AB subtends angle E1. You see this chord AB subtends angle C1. So that means C1 and E1 are equal. They are both equal to what? To 40 degrees. Why? Angles in same situation. Or seg. Let's move on to the next one. Angle C2. So you update, guys, the diagram. Whenever you get answers, you update. E1 now is 40. C1 was already 40. Now let's continue. Angle C2. Where's angle C2? Angle C2 is here. Angle C2. Titus is saying angle E1. Yeah. We sorted that one out. We sorted that one out. I just want to find out now, what is C2? What is C2? Oh, sorry about that, guys. We wanted to get the angle C2, right? So there is angle C2. So I guess I was still asking you guys, C2. How do we get C2?